All right, let's go ahead and go through some of these problems. First is composite functions. And with our composite function, looking at the original problem, we're shown that the graphs of the equation, we have a y equals f of x graph and a y equals g sub x graph. So here's g, here's f, and then we're asked which of the following best approximate the value of f of g of 4. All right, well, we want to start with the innermost. So we're going to calculate as an input of 4. So we're plugging 4 in as an input to g, and we want to know what comes out as an output. Whatever comes out as an output, we're going to plug that into our f function and then look at what its output is. All right, so 4 on the g. 4 on the g. So 4 is an input, that's your x. 4 on the g is right here. And then we look what the output is. The output, or the y value, is -8. So out comes -8 when you plug 4 in for g. Then we kind of reset ourselves, and now we do the same thing for f at -8. So here's our function. We're looking for -8 as an input. That's the x values. There it is right there. That's our input of -8. And then we look for the output. The output is -8 for this one. So that should be our answer. Let's check. Got it. See if there's any others that are kind of tricky. This one's done exactly the same way. My suggestion would be to rewrite this function in terms of f of g of 9, and that just makes a little bit more sense. Following our order of operations, we would calculate this one, plug that answer in, and find out what the output for f is. All right, not too bad on this one. So we'll go ahead and let those go. All right, find composite functions. All right, so this is where we're doing the algebra, and basically we're asked to simplify this. All right, let's get the old pin going. All right, f of h of x. So f of h of x. And I'll go ahead and use my little skeleton here. This is the f function, so whatever we plug in there, we cube it, and then we're going to subtract 6 from that. All right, so inside there is our h function. Here's our h function right there. So we're going to be plugging in the cube root of 2x minus 15. All right, wherever I see a parenthesis, that's what I plug in. So in here, we're plugging in the cube root of 2x minus 15. Now these undo themselves. So the opposite of a cube root is cube, or the opposite of cube is cube root. So those undo themselves. But one of the things I wanted to do is I wanted to make sure that you saw a different way to represent this. So I'm going to go ahead and just write it in a different way so we can kind of get used to some of the algebra that you need for more advanced problems like this. So the cube root is the same thing as what? How can I rewrite the cube root? Do you remember? What kind of exponent is right here that means cube root? Well, it's the 1/3 power. It's a fractional exponent. Whatever kind of radical right here there is, that's the denominator for the fractional exponent. That's the bottom of the fraction on the exponent. So usually we have square roots, so that would be most commonly a 2 down here for square roots. And then all of this is still to the 3rd power, and it's minus 6 at the end. All right, so this is kind of what I wanted to show you. A power to a power means multiply. So just like these undo themselves, a power to a power would give us 2x minus 15, and it's to the 1/3 times 3 is 3 over 3 minus 6. 3 over 3 is just to the first power, so that just goes away. Anything to the first power is itself. So all of this turns into 2x minus 15, and then we still have the minus 6 here. So basically we're just dropping the parentheses. That was pretty nice. Combine like terms, negative and a negative make a bigger negative. This is 2x minus 21. That's what I got. So it simplifies. Let's see how we did. 2x minus 21. Go for it. Got it. All right. So it's about simplifying, and this one's not too bad to deal with the radicals or the root signs, but it's algebraically, and as we get more advanced, it's much better to look at it as fractional exponents. All right. Check. All right. Modeling with composite functions. Let's go. All right. Let's see what we're dealing with here. Iami plans to go blueberry picking before school, which starts at 8 a.m. The amount of blueberries B in cups that a Yumi picks, given that she starts picking T hours after 12 a.m. This is given by the function B sub T is equal to 2 times 8 minus T. Okay. After school, she plans to bake blueberry muffins with her pickings. The number of muffins M that she can bake within cups of blueberries is given by this function. Find the explicit expression that gives the amount of muffins a Yumi can bake given that she starts picking T after 12. Okay. Give the explicit expression. So we're looking for basically the simplified version of all this put together. All right. Given the number of muffins, so we're looking at it as a function of muffins. How many muffins come out? Gives the number of muffins. So it's going to be like as an output, as the final function is muffins, can bake given that she starts picking T hours after 12 a.m. All right. After 12 a.m., she has this function right here. So it looks like we start out, and then it's just nice to kind of go through what each of these are and see how they relate. So what does T represent? Given that she starts picking T hours after 12. So however many hours after 12, that would go in here. That's your input for the original, is given by the function. And then this tells you the amount of blueberries in cups. So we're going to get those blueberries in cups after this as an output here. And then she plans the number of muffins M she can make within cups of blueberries. So that links together. However many cups of blueberries she gets from here, we stick that into the muffin function, basically, and that'll give us our final output. Okay, so the explicit expression, we're plugging basically the numbers in for here. I'll go ahead and switch colors. So I'll just take it a little bit easy. First, we'll go for the innermost function here. B sub T is 2 times 8 minus T. All right, there's that function. And then we're plugging all of that into the M function. The M function is just basically multiplying by 12 here. So this is going to be equal to 12 times whatever's inside that parenthesis. Looks like I ran out of room, which is 2 times 8 minus T. All right. And okay. So 12 times this explicit function. Do they want me to simplify? I'm not sure. Let's see. We can multiply this out if we need to, but first let's try the function just as it's given, one inside the other. And they already ended the parentheses for me. Check. Got it. So you didn't have to simplify on those, so that's pretty nice. All right, these are kind of tricky. Let's check out the next one. All right. Lena studied her farm where she identified several quantitative relationships and modeled them with the following functions. All right. The good thing, or the thing you have to focus on here, is to make sure everything links together on them. All right. Let's see if we can't link them together. The S R sub x function, S of R of x, represents which of the following? All right. So we're starting with the x. The amount of rainfall, x, okay, that gets plugged in, and that comes out, and we have to be careful. Sometimes they're tricky if things don't link together, so we definitely have to make sure they link together. So the x goes into the r sub x function. That's what we have here. We got the r sub x function, starting with x, and then we want to look at r sub x is the amount of rice grown. The amount of rice grown, that's this function right here, is in terms of n. So the amount of rice grown, and then you would usually plug in the n sub k, the amount of rice noodles produced, and then you can get to s. Okay? So they're skipping n right here. They skipped They skipped that n function. That seems like an issue. So let's just go through these and see what they kind of represent. That might help us with future problems like this. But it looks like it's a none of the. It looks like it's a none of the above. But let's just look. Let's change colors. The amount of rice noodles produced. So the amount of rice noodles produced, that's the S function, as a function of the amount of rainfall. As a function of the amount of rainfall. Well, that's the same thing that we got, but remember, it doesn't link to it. The amount of rainfall in the amount of rice grown does not link to the S function. So we would have to travel through n first to get here. So for this to be proper, it would be S, and we have to go through n first to get it. And then it's the R. And then the initial would be X. So this is what it should look like, where we have our input of X as the amount of rainfall, check. Then that turns into the amount of rice grown. So there's the amount of rice grown there. Then that turns into the amount of noodles produced. So that's what we're missing, the amount of noodles produced. You can't just jump from R to S. So we're missing the amount of noodles produced. And then we can go ahead and it would be the consumption of the soy sauce. All right. Let's just look at each one of these. Consumption of soy sauce is S of T. Won't let me write S of T. And then as a function of the amount of rice grown, as the amount of rice grown, N of K on that one. So that's what the second one represents. And consumption of soy sauce, which is S. Consumption of soy sauce. Won't let me write anymore. So consumption of soy sauce as a function of the amount of rainfall. Consumption of soy sauce, S of T, as a function of the amount of rainfall. So once again, they're skipping that N. We need that N. So none of the above on this one. All right. So everything has to link together. So that's the key, is you have to follow the trail. If there's any jumps in the trail, it's no good.